Great to see you here again in this new video. We're going to look at modular exponentiation. When we look at the modular multiplication, we know that we have the different rules for multiplication. So the product of A times B modulus M can be written as A modulus M times B modulus M, and we take the modulus M of that. Now, when we multiply, for example, 246 with 35 modulo 13, this will give 246 times 35 modulus 13, and then we first calculate 246 modulus 13 multiplied with 35 modulus 13. So what we have here is we calculate 246 modulus 13 and 35 modulus 13, we multiply them, and then we apply modulus 13 on that product. So when we look at 246, we can say it's 18 times 13 plus 12. This means that 246 modulus 13 is 12. 35 modulus 13, we can say that 35 is equal to 2 times 13 plus 9, which gives us 35 modulus 13 equal 9. And now we can replace 246 modulus 13 by 12 and 35 modulus 13 by 9. So we find 246 times 35 modulus 13 is 12 times 9 modulus 13, which gives us 4. So basically, we have this rule of the modular multiplication, which will help us to do those modular multiplications in a more efficient way. Now, when we look at modular exponentiation, we are going farther than multiplication. We are going to take a power of the number. So what we are going to have is a to the power n modulus m is a modulus m to the power n modulus m. So basically, we're going to use this as a way to deal with those powers. Now, the problem is that when we look at the term a to the power n, which can become very large very fast, and it is possible that these things will create a memory overflow in the computer or the calculator, and a memory overflow will give, in fact, an error, and your project or your program is not working properly. Now, consider that we want to find 3 to the power 95 modulus 13, and we have a computer which can give numbers up to 3 to the power 55. Now, how do we do this? Well, we can say that we have 3 to the power 95 is 3 to the power 45 times 3 to the power 55. And what we're going to do, we're going to use the rule of the modular multiplication to this product. And we can say that 3 to the power 45 times 3 to the power 55 modulus 13. We can split that up as a product of 345 modulus 13 and 3 to the power 55 modulus 13, and we take the modulus 13 on this. The fact that both numbers 3 to the 55 are lower than the limit, so we can calculate this number. But there are better ways to deal with this. The first thing what we're going to look, let's have a look on these operations with the binary expansion. Now, the cryptography is using modular exponentiation, and it's important to find b to the power n modulus m efficiently, where b, m, and n are large integers. So basically, we need that calculation. Now, the calculation of the first term, b to the power n, is with what we do first, and then we find its remainder of its division by n. Now, when we look at the binary expansion, it will be a more efficient approach to do this operation. Now, when we use the first element b to the power n, we can replace this by the binary expansion of n. So we're going to write n as a binary expansion, which means that we can say that b to the power n is equal to b to the power of the binary expansion of n, which means that we have in fact b multiplied with the powers of these different elements, these different components of the binary expansion. So when we say b to the power a k minus 1 times 2k minus 1 plus up till a1 times 2 plus a0, we can write this as a product of b to the power ak minus 1 times 2 to the power k minus 1 multiplied by b to the power ak minus 2 times 2k minus 2. And we continue that till we reach the last terms, and we find for the last, let's say the before last term, we find b to the power a1 times 2 times b to the power a0. And that's in fact what we are going to calculate. Basically, we have to calculate b to the square, b to the 4th power, b to the 8th power, up to b to the 2k power. And we find that the coefficient ag are in fact 1 where we have them. So we only calculate them for the parameters where ag, the coefficient, is equal to 1. Of course, when it's equal to 0, we don't have to calculate it. So let's have a look when we have n which is equal to a power of 2. And k is, of course, larger than 1. So when the exponent of is a power of 2, then we can find a to the power n mod m in an easy way. And we will do it with an example. Just imagine we have 8 to the power 256 modulus 13, and we know that 256 is 2 to the power 8. We can say that a modulus 13 is 8. There is 8 is 0 times 13 plus 8, so 8 is the remainder. 8 modulus 13 is 8. Now we can say a to the square. A to the square modulus 13 is a modulus 13 times a modulus 13 of modulus 13. So we have 8 times 8, which is 64, modulus 14, which is 12. You can calculate it easily by hand and then continue to the next step. A to the power 4 is modulus 13. Now we multiply a to the square modulus 13. We take the power of 2 of them, so we find that this is 12 times 12. Finally, we find 144 modulus 13, and this is equal to 1. Then we have 8 to the 8 modulus 13. We have 1 times 1, so we have 1 modulus 13, which is 1. And basically, 8 to the 16th modulus 13 is 8 to the 8 modulus 13 times 8 to the 8 modulus 13. So both of them are also equal to 1. So we find again 1 modulus 13, which is 1. And 8 to the 256 is in fact modulus 8 to 56 modulus 13. When we continue, all of them are equal to modulus 1. So we have 1 modulus 13 is 1. So finally, that's how we find the final power of this number. Now what we have, 256 is 2 to the power 8. So it's going very easy for the calculation because we have those powers and we find the last element here. Now, another number, when we have another number n, we can find the binary notation of that number. So basically, when we select a number, a to the power n, we can find the binary notation of n. So basically, when we say that we have 5 to the power 115 modulus 13, we can find that the binary expansion of 115 is 0, 1, 1, 1, 0, 0, 1, 1. Now, this means we can write as 115 as 2 to the power 0, plus 2 to the power 1, plus 2 to the power 2 coefficient is 0, so that's 0. 2 to the power 3 also has a coefficient 0, so it's also 0. The next term we have is 2 to the power 4. Then we have 2 to the power 5 and 2 to the power 6. So basically we can say that 115 is 1 plus 2 plus 16 plus 32 plus 64. And basically we have to find the expansions for 5 modulus 13, that's the first one, 5 to the square modulus 13, 5 to the power 16, and so on, up till we reach 5 to the power 64 modulus 13, and then we can calculate the final result. Let's see how we get this done. So basically what we get now is that we are saying that 5 modulus 13 is 5. Okay, so now what we do, we say 5 to the square modulus 13 is 5 times 5, so we have 25 modulus 13, which is 12. Now 5 to the fourth modulus 13, so I have to multiply twice 5 to the square modulus 13, which is 12. 12 times 12 is 144, so 144 modulus 13 is 1. Then we have 5 to the power 8 modulus 13 is again 1 modulus 13, because I have 1 times 1. 5 to the power 16 is again 1. 5 to the 32nd modulus 13 is again 1 modulus 13, because we have 1 times 1 is in fact 1. And then we have 5 to the power 64 modulus 13 is 1 modulus 13 is 1. And when we put this all together, we have in fact the 5 to the power 115 modulus 13 is 5 times 12 times 1 times 1 times 1 modulus 13. This is 60. So 60 modulus 13 is 8. So basically what we did is all those high, let's say high numbers, we reduced to smaller numbers by every step, calculating the equation and in fact finding the mode or the module for each of those numbers. So basically we avoid that we have all those large numbers, and we can find the number 5 to the power 115 modulus 13 in a, let's say, acceptable way without causing any overflows in the program. We can also put this into pseudo code. We have the modular exponentiation that we have. We have the integer with those parameters. We start with x equals 0. We indicate we have a variable power is b modulus m. For j from 1 to k minus 1, so we go over all the parameters of the integer, so all the parameters a0 up to ak minus 1. When aj is 1, then we have x is x times power modulus m, and we rename that power is power times power modulus m, and we return at the end x equals b to the power n modulus m, so we find the final value of this expression. Now you can do this step by step. It's basically what we did in the previous example. We in fact applied the code like it is written here. So that's what I wanted to say about modular exponentiation. It's a very important thing to understand it. We will use it later when we are dealing with the cryptography. Now this was the last part of this session of 3 videos related to the different expansions of numbers and modular calculations. In the next video, we'll be looking at primes and the greatest common dividers. You're doing a great job, and I'm looking forward to seeing you in our next videos. Thank you, and bye-bye.